Hello everyone, this is Liyuan Liu. It's my great honor to introduce our project, Understanding the Difficulty of Training Transformers. This work is conducted together with Dr. Xiaodong Liu, Dr. Jianfeng Gao, Dr. Weizhu Chen, and my advisor, Dr. Jiawei Han. Transformer has been quite popular recently. However, its training requires additional, non-trivial efforts. Firstly, although SGD is a canonical algorithm for conventional neural networks, it fails to train transformers effectively. And also, we found that removing the warm-up phrase results in more serious consequences to transformer training than other architectures. In our study, we endeavor to understand what complicates transformer training. And it starts from the observation that the pre-layer norm transformer is more robust, while the post-layer norm transformer usually have a larger potential. Pre-layer norm and post-layer norm are two variants of transformer architectures, where the pre-layer norm puts the layer norm inside of the residual block, while post-layer norm puts layer norm outside of the residual block. In our experiments, we did a hyperparameter study on both architectures, and we found that pre-layer norm converges in all 15 combinations of hyperparameters, while post-layer norm training diverges in about half of them. And also, if this post-layer norm converges, it usually leads to a better BLEU score than the pre-layer norm architecture. So in other words, we found pre-layer norm variants are more robust, while post-layer norms usually performs better. Also, we visualize the learning curve of the 6-layer transformer on the right, so we can find that although this post-layer norm architecture converges a little bit slower at the beginning, it actually converges faster in the late stage of the training. And also, when we want to train this 18 layers transformer, the post-layer norm architecture directly diverges, while the pre-layer norm architecture converges well. In the literature, gradient vanishing has been long regarded as a major reason destabilizing model training, since it can hamper the training from the beginning, and a recent study shows that even after introducing residual connections, the transformer network still suffers from gradient vanishing. But surprisingly, in our study, we found that gradient vanishing is not the direct reason causing the unstable transformer training, since we observe fixing the gradient vanishing issue alone cannot stabilize training, and also unbalanced gradients issues are largely handled by adaptive optimizers. We first theoretically established that only the post-layer norm decoder suffers from gradient vanishing, but neither post-layer norm encoder or pre-layer norm encoder or decoder. We also empirically verified our findings by visualizing the gradient distribution of 18-layer post-layer norm encoder-decoder and pre-layer norm encoder-decoder. As visualized in the middle, we can find that only the post-layer norm decoder suffers from gradient vanishing, as its parameter gradient keeps decreasing in the backpropagation from 18th layer to the 4th layer. With more analysis, we found that actually the gradient vanishing only happens in the backpropagation for the post-layer norm encoder attention sublayers. Therefore, in the post-layer norm architecture, if we change the decoder from post-layer norm to pre-layer norm, it can actually fix the gradient vanishing issue. But the resulting hybrid transformer, although not suffering from gradient vanishing, its training still diverges. It implies that there are other factors influencing transformer training greatly. We also observed that unbalanced gradient issues are largely handled by adaptive optimizers. We first visualized the gradient norm distribution for parameters in the self-attention modular in an 18-layer pre-layer norm transformer encoder in the bottom. We can find that different parameters have very different gradient norms, and also different layers have very different gradient norms. We also observed that even with this very unbalanced gradient distribution, the adaptive optimizer successfully assign different learning rates to different parameters and leads to consistent update magnitudes for different parameters. This parameter update norm is calculated as the absolute difference of two consequences checkpoints. These two phenomena verifies our intuition that unbalanced gradients are not the root reason causing the unstable transformer training. Here we go beyond existing literature and identify an amplification effect that influences training greatly. Specifically, we found that over-large reliance on residual branches would amplify parameter changes and result in significant output fluctuations. Specifically, comparing the post-Leonarm and pre-Leonarm architecture, we found that their major difference is they aggregate residual branch outputs differently. For the pre-Leonarm architecture, they aggregate different residual branch outputs by the same Leonarm, where for the post-Leonarm architecture, it aggregates different residual branch in different manners. We employ beta ij to further illustrate their difference, which integrating all the scaling effects from the Leonarm and captures layer dependency. Specifically for residual layer x plus fx, we refer fx as the modular outputs and x plus fx as the layer outputs, which integrates the modular outputs and shortcut connection. In a residual network, we can represent the input of I plus 1's modular, which is also the output of the S layer as a weighted sum of the normalized output of all previous residual modulars. And beta ij is the weight used in this weighted sum. For example, in the pre-Leonarm network, the beta ij is calculated as the ratio between the standard deviation of the jth modular's output and the standard deviation of the sum of the first I modular's outputs. We theoretically established that the model output change after changing the model parameter from W to W plus delta is related to the dependency on its own residual branch, which is the weight for the S residual outputs in the S layer outputs. Based on these results, we can get that for pre-Leonarm, the model output change is in a log-n relationship with the number of layers, where for post-Leonarm architecture, the output change is in a linear relationship with the number of layers. We further conduct experiments to verify our theory matches real-world situations. We first estimated the model output change after changing model parameters with random perturbations for 1-layer transformer to 100-layer transformer at initialization. We can observe that the relationship between the output change and number of sublayers is O(n) for post-Leonarm and is O log n for pre-Leonarm. And we also use R-square to estimate the significance of this relationship and found R-square equals to 0.99 in both situations. We also estimate the model output change with updating the model parameters with gradient updates, and we can observe a similar phenomenon that the post-Leonarm is less stable than the pre-Leonarm, and R-square equals to 0.75 for both post-Leonarm and pre-Leonarm in this situation. Intuitively, large output change indicates the training to be unstable. Comparing the loss surface between the VGGNet and the ResNet, we can find the loss surface of this ResNet is much more smooth. In other words, after changing the parameter a little bit, the output will not change dramatically. At the same time, intuitively, a very large output change indicates the problem is likely ill-conditioned. Our theory can also help to interpret why warm-up helps to alleviate the instability of post-Leonarm. In our previous theory, the constant C is related to the gradient norm, which will be smaller in the late stage and will be larger in the early stage. So in other words, in the early stage of the training, the model output change will be more dramatic, and it will be helpful to use a smaller linear rate. However, we also found that the difference between O log n and O(n) is significant for deep networks or large N. And in our experiment, simply increasing the warm-up steps fails to stabilize the training of 18-layer transformer successfully. To better understand the difference between post-Leonarm and pre-Leonarm, we visualize their encoder's layer dependency at both initialization and after 100 epochs. This x-axis here indicates different residual branch outputs, and the y-axis here indicates different layers outputs. For example, x4 here indicates the output of 4th layer, which is also the input of 5th layer. And x4 here is a weighted sum of A1, A2, A3, and A4. And we realize their weights in different colors in these 4 different figures. And we can find that x4 here have large dependency on A4, its own residual branch. And at the same time, in the pre-Leonarm, we can find that this x4 here has roughly the same dependency on the previous 4 different residual branch outputs. We can also find that in this 100 epochs training, as the model becomes stronger and stronger, these layers learn to depend more on its residual branch outputs. Also, comparing their final models, we can find these post-Leonarm layers have larger dependency on their residual branches than the pre-Leonarm networks. In our previous analysis, we have established that the relative small reliance on its own residual branch of pre-layer norm at initialization helps to stabilize its model training. We also know that the post-layer norm has a better performance than the pre-layer norm in the late stage of the training. Therefore, we further hypothesize that a heavy dependency on its own residual branch allows the model to have a better performance. Accordingly, we propose admin initialization for the post-layer norm architecture. Specifically, we add omega I to restrict the layer dependency in the early stage and allow the model the flexibility to change its value to have larger reliance on its own residual branch in the late stage of training. Specifically, we divide the initialization to two stages to fit different training settings. First, we would initialize all omega I as 1 and empirically estimate the invariance of the outputs of each residual branch. And then, based on the estimated variance, we would initialize this omega I accordingly to ensure the output change is subject to log-n relationship at initialization. We also verify this log-n relationship empirically, as in this figure and this figure, we can find that although this admin method is based on the post-layer norm architecture, its output change is in the same scale with the pre-layer norm architecture at initialization, which is much more stable than the vanilla post-layer norm architecture. With the help of admin, we successfully trained an 18-layer post-layer norm transformer for the translation task. Here we realize their encoder's layer dependency both at initialization and after 100 epochs of training. And we can find that admin successfully stabilized model training at initialization by avoiding overlarge dependencies. And after employing this admin initialization, we can find the post-layer norm's layer dependency is very similar to the pre-layer norm layer dependency. And also, in the late stage, this post-layer norm architecture allows the model to have a larger dependency on its own residual branch. In our experiments, our proposed admin method consistently stabilizes model training and leads to faster convergence and also better performance. Our proposed admin method consistently outperforms its post-layer norm and pre-layer norm baselines in all 6 different settings. It's also worth mentioning that without introducing any hyperparameters, our proposed admin method achieves a new state-of-the-art on the long-standing WMT14 English to French dataset. We further conduct systematic analysis on these 72-layer deep transformers and summarize the results in the following report. And here are some highlights. Firstly, if we are using back translation to train the model, we can actually achieve a 46.4 BLEU score on the long-standing WMT14 English to French dataset. And also, if you apply this 72-layer transformer on the WMT14 English to Germany without using back translation, we can get 30.1 BLEU score, which is also very good. We also conduct the hyperparameter study on the learning rate and the beta 2 for the second momentum calculation. And we can find that with the help of our proposed admin method, this post-layer norm converges in all 15 combinations of hyperparameters, and also it leads to a better performance. Here are a few takeaways from our study. First, we show that unbalanced gradient issue is not the root cause of the unstable transformer training. And also, these unbalanced gradient issues are largely addressed by adaptive optimizers. We also show that large dependency on residual branches amplifies the fluctuation and destabilizes the model training. And by controlling such dependency at initialization, our proposed admin method is more stable, converges faster, and leads to a better performance. Thanks for your time.